happy to hear about your talk, Louise, about the Cepheids distance scale from the local Gaia calibration to distant galaxies.
May I start? Okay. Today, I will talk about the work I have carried out at Paris Observatory during the last 3 years. And my work is entitled The Cepheids Distance Scale from the Local Gaia Calibration to Distant Galaxies. The outline of the presentation is the following. In the first time, I will recall how Cepheids stars are used to measure distances in the universe and their place in the tension on the Hubble constant. Then I will describe the main 2 results of my PhD thesis, the first one being the calibration of the Cepheid-Leavitt law with the Gaia mission and the re-evaluation of the Hubble constant. The second result of my thesis is the calibration of the metallicity effect on the PL relation by comparing its calibration in the Milky Way and the Magellanic Clouds. Finally, I will conclude by mentioning 2 recent papers and by giving some perspective for future improvement of the distance scale. First, how distances are measured in the universe. Distances are probably one of the most difficult parameters to measure in astronomy. About 1 century ago, astronomers didn't know exactly how to measure distances. They didn't know the size and the structure of the universe. But Henrietta Leavitt made a significant discovery. She was studying Cepheid stars, which are pulsating stars, in the small Magellanic Cloud. And by classifying those stars, she noticed that the brighter variable stars have the longer periods. This relation is now called the period luminosity relation, or the Leavitt law. And it has strong consequences on many other discoveries. Because it means that if you know the period of a Cepheid, which is easily measurable, you can directly determine its distance. At that time, there was a great debate between Shapley and Curtis. They were observing spiral nebulae in the sky, and Shapley believed that they are all inside the Milky Way, while Curtis believed they are outside and they are different galaxies. So using Leavitt's relation and Cepheids, they finally answered this question and put an end to this debate. So at the end, Curtis was right. These galaxies are outside of the Milky Way. A few years later, it was Edwin Hubble who used the Cepheids and this relation with Cepheids to measure the velocity and the distance of galaxies. And also by classifying them, he discovers that the most distant galaxies are moving away from us at greater speeds. This is the discovery of the expansion of the universe. Today, the ratio between the velocity and the distance of these galaxies is called the Hubble constant and is written h0. So now a few words about Cepheid stars. Cepheids are located in a region of the HR diagram, which is called the instability strip. It also contains other pulsating stars of different periods, but with the same pulsation mechanism. Cepheids have a period of about from 2 to 100 days. They are intermediate to massive stars, but most importantly, they are very bright. Their brightness changes during a cycle by up to 2 magnitudes in the optical, but also the color changes during a cycle. And Cepheids are considered primary distance indicators. In the distance scale, there are several steps, and Cepheids are at the very beginning. The first step of the distance scale is here on the left. It's the Milky Way. So the first step is to measure distances to Cepheids geometrically. For example, with the parallax, this is what Gaia does. We look at the movement of a star in the sky during 1 year. Or we can measure the distance to Cepheids in the Magellanic Clouds by the method of detached eclipsing binaries, as it has been done by the Gaia project. And with these geometrical distances, we calibrate the Cepheid period luminosity relation. The second step of the distance scale is to observe nearby galaxies where we can observe Cepheids and type 1a supernovae, which are secondary distance indicators. And using the PL relation, we calibrate the brightness of the supernovae. Finally, the third step is to observe galaxies in the Hubble flow, which means galaxies moving away from us under the effect of the expansion of the universe. Using the supernovae, we measure their distances, and from the redshift, from the spectroscopy, we obtain the redshift, and then comparing the velocity and the distance gives the Hubble constant. So Cepheids are really the first step of this distance scale. It means that even though they are observed locally, they have strong implication at larger scales and in cosmology. Today, the value of the Hubble constant is widely debated. This plot represents its value over the last 20 years. First, the blue measurements are from the Cepheids supernova method that I just described. So first, it was around 72, and it has always stayed quite constant over time. And now we have a very precise measurement from the SHOES team, about 73. The second method represented in red is from the temperature fluctuations in the cosmic microwave background. It was observed by Planck, and this method is based on the standard cosmological model, which is also called the lambda CDM model. And it gives a lower value of 67. So today, the difference between the late measurement in blue and the early measurement in red is what we call the Hubble tension. It's about 4 sigma. In green, I also represented an independent measurement from tip of the red giant branch stars, which replace the Cepheids as primary distance indicators to calibrate the supernovae. And it gives a lower value around 69. And it doesn't explain why between Cepheids and Planck there is this 4 sigma tension. So it's really interesting to compare these two methods, the late and the early measurement, because it's a powerful test of the standard cosmological model. And if this tension is confirmed, it would suggest that the standard model should be slightly revised by, for example, including exotic particles or new physics beyond the standard model. In order to understand this tension, the aim of my PhD was to investigate the Cepheid distance scale and its calibration. And for that, we need extremely precise distances. And this is what Gaia provides. Before the Gaia mission, we could measure trigonometric parallaxes, first with Hipparcos. Hipparcos provided a large number of parallaxes for Cepheids, but they were of quite low precision. But later, with the Hubble Space Telescope, it was possible to measure first with the fine guidance sensor and then with the wide field camera 3 to measure Cepheid parallaxes with a better precision, but only for a small number of Cepheids, because it was quite expensive in terms of observation time. But now we have Gaia. Gaia data were published in several data releases. The first one in 2018. The second one when I started my PhD. And the early data release 3 was published in December of 2020. So we have now good precision astrometry for a large number of stars. Of course, all of them not all of them have a good, excellent precision astrometry, but still it's way better than with Hipparcos and Hubble combined. We will also have radial velocities, and we already have multi-band, multi-epoch photometry in 3 broad optical bands. Before applying Gaia parallaxes to calibrate the Cepheid distance scale, a few issues have been raised with Gaia data. First, the parallaxes are subject to a 0-point offset. There was a correction proposed by Lindegren, and it takes into account the magnitude, the color, and the position on the sky. And other corrections were also published a few months ago. And it's really interesting because now we can compare all of them to check their consistency. A second issue is saturation. Cepheids stars are very bright, so many of them are saturated in Gaia detectors. One solution is to adopt a quality criteria from Gaia, which is the renormalized unit weight error. It should be around 1 in the ideal case, but for saturated stars or outliers, it is over 1.4. So a good solution is to eliminate these stars with higher than 1.4. And the second solution is to find faint companion stars in the close neighborhood of Cepheids and adopt their parallaxes instead of that of their Cepheids. The color variation is also a problem for the astrometry, because the position where the light hits the detector depends on the color of the star. So if the color is varying, it produces additional noise in astrometric measurements. So to solve this problem, we can find non-variable stars associated with Cepheids and also adopt their parallaxes. A first idea was to find close companions among the sample of Kervela 2019. I selected 22 candidates of Cepheids with resolved companions. They are not variable, they are not saturated, and also they are not sensitive to the flux of the Cepheids. As you can see on this plot, I represented the G-band apparent magnitude of the Cepheids in dark blue, and that of the companion in light blue as a function of the parallax. And in blue is the saturation zone. So many Cepheids are close to this saturation zone, while the companions are in the optimal range, optimal regime for Gaia between 12 and 18. There is no saturation issue and it's not too faint. So combining these 22 companion parallaxes with ground-based magnitudes in optical and near infrared, I corrected the magnitudes from the extinction, and I derived the astrometric-based luminosity in order to stay in the parallax space and not invert them. And then I applied the Monte Carlo algorithm to fit the A and B coefficients of the PL relation. So first I did this test with Gaia DR2 parallaxes. This is what I published in my first paper. And this is the comparison. The top plot represents this calibration with Cepheids and the bottom plot with companions. So you can see the reduced chi-square is a bit higher with Cepheids. There is one outlier here that was excluded. And here with companions, the reduced chi-square is lower and the dispersion is similar. So it shows that with Gaia DR2, using companions instead of the Cepheids to calibrate the PL relation is really promising, and we have a gain in terms of precision. In my thesis, I updated this result by replacing DR2 by EDR3 parallaxes. And this is the result. So now we have a lower dispersion with Cepheids. The blue squares are first overtone Cepheids. They are converted here. We can either convert them or exclude them, but here they are in quite good agreement with the fundamental mode Cepheids, so I made the choice of including them. And with companions, we now have more outliers. So this test suggests that the variation in color of Cepheids does not impact anymore the quality of the astrometry. It suggests that we can now use directly Cepheid parallaxes from Gaia DR3. The second idea was to find Cepheids in open clusters. I cross-matched a catalog of open clusters with the Cepheids from Gaia. I cross-matched the parallaxes, the coordinates, and the proper motions. And I found first a sample of 14 candidates that I complemented with 6 from the literature. And the cluster members are not variable usually, and on average, they are fainter than Cepheids. And we have a huge gain in precision by averaging over all the members. However, we have to take into account other effects. So this is the equation that gives the total uncertainty on the parallax of the cluster. It depends on n, the number of stars, on the individual uncertainties of each member. On this factor k, which is an overestimation factor, it's basically it's about 1.6. And here the last term is the most important one. It's the largest, and it is due to angular correlations in the sky, because all cluster members are located in the same region in the sky, so there is an important term of correlation to take into account. When I compare the PL calibration from Cepheids and from clusters, we can see that the dispersion from cluster parallaxes is lower. 0.09 mag is very close to the width of the instability strip. It shows that this is one of the best calibration that we can obtain. And of course, we have a lack of long period Cepheids, as always in the Milky Way. But by comparing the slope of this calibration with others from the literature, it is quite consistent. Then I wanted to analyze the impact of this sample of Gaia parallaxes on the Hubble constant. This is a table taken from Rees 2016, which gives different H0 values from different distance indicators, from masers, from Cepheid parallaxes, and from eclipsing binaries. And they combined all of them into an average value of 73. So I'm just interested in the one from Cepheid parallaxes, which is 76. It's a bit higher than other distance indicators. And these parallaxes were from HST and Hipparcos. So I replaced Gaia previous parallaxes by Gaia parallaxes. This is the procedure. H0 Gaia is what we want to evaluate. This is the parallax from Gaia, and H0 initially is 76. To derive the predicted parallax, I used this equation between parallax absolute and apparent magnitude in the Wesenheit index. And the absolute magnitudes are derived from this equation, the PL relation published by Rees, which is slightly modified because they published the relation that corresponds to this average value. So I just offset the intercept, so it's consistent with only the calibration in the Milky Way. And by applying this procedure, I obtained a lower value of 73, which is lower than the initial value, but also in better agreement with other distance indicators. The uncertainty is still low because it does not include yet the systematics due to the 0-point offset. I should evaluate this systematic, for example, by comparing different correction, the one from Lindegren and others. In my first paper with DR2, this systematic was of 1.9. So now with DR3, I estimate it's lower than 1.5. So changing the data, changing the parallaxes in the H0 calibration doesn't seem to solve the tension. There is still a 3 sigma tension with the Planck prediction. So it's a very interesting test to see the influence of the data on the results on the Hubble constant. In summary, I have calibrated the PL relation without Cepheids, but instead by using companion stars and open clusters in order to avoid saturation and color variation. It seems that the contamination of the astrometry due to the change of color is now globally averaged in Gaia EDR3. We obtained a very low dispersion of the PL relation, especially with clusters. And we obtained a new value of the Hubble constant, which is consistent with other distance indicators and still in 3 sigma from Planck. This study has some limitations. First, the companions are now too faint for this analysis. so they are not competitive anymore with the Cepheids. Open clusters gives very precise parallaxes, but are limited by angular correlations. The photometry that I used is taken from ground-based telescopes, and it introduces systematics in the photometry because in other galaxies, the Cepheids are observed mostly with the HST. So we are combining different photometric systems. We have to correct for the reddening. This is why we mostly use near-infrared or Wesenheit indices. There is still a 0-point systematic in Gaia EDR3, but it's now better calibrated. And we have to take into account other systematics on the distance scale. One of them is the effect of metallicity. And this is the effect and the main systematic I wanted to study in my second paper. So to improve the calibration of the distance scale and of H0, we need to study all these systematics. It can be on the Cepheid distances, Cepheids photometry, or the calibration of the PL relation itself. So the metallicity effect is, you can consider it as a third term of the PL relation. It's called gamma. And here I assume there is no metallicity effect on the slope, but only on the intercept. But of course, we can also study the effect on the slope. From theoretical studies, most papers found a gamma which is positive, which means that metal-rich Cepheids are fainter than metal-poor Cepheids. Basically, this is because when a star is metal-rich, it has more lines. So basically, the flux is lower and the star is fainter. However, empirically, many studies reported a negative gamma sign, meaning that metal-rich Cepheids are brighter. On this plot, I represented a few estimates from the literature on the metallicity effect empirically. First, in green, it's the work by Friedman et al. They combined individual metallicity values in the LMC. They obtained in the mid-infrared, so here is the negative sign. In the mid-infrared, they obtained a negative value with a quite strong effect. Going to the near-infrared, the effect is close to 0 and it becomes positive to the optical. In orange is the estimate from Wilgorski. They performed a differential analysis between the LMC and SMC PL relation and obtained an effect close to 0, but still on the negative side. In red is the value from Giren. They performed a Bade-Wesseling analysis of Milky Way LMC and SMC Cepheids by deriving the distance to each Cepheid, and they obtained a negative value, which does not depend on the wavelength. And finally, very recently, Ripepi published new measurements of metallicities for Milky Way Cepheids, and they derived a very strong effect with a negative sign in the K-band, meaning that metal-rich Cepheids are brighter. But it's difficult to compare these results because all of them are using different distances for the LMC and the SMC, and even in the Milky Way. They use different samples of different size and different metallicities, either average or individual. So it's very difficult to compare them. So in the first place, I took a sample of Milky Way Cepheids. For the photometry, I adopted well-covered light curves in optical and near-infrared from ground-based telescopes. I complemented this sample with Gaia and Spitzer light curves, which is not present in my second paper, but it was updated in the thesis. For the distances, I adopted Gaia EDR3 parallaxes directly and corrected them for the 0 point. And for the metallicity, I found several catalogs that I combined to adopt individual metallicities with an average of a little bit higher than solar metallicity. And the spread is 0.4 dex for all Milky Way Cepheids. So adopting these values, I calibrated the PL relation, and I plot on this diagram the intercept of the PL relation as a function of metallicity. I fitted a straight line in these points by taking into account the uncertainties on both the intercept and the metallicity. So the trend is not obvious, but from a Monte Carlo simulation, I obtained a negative sign of the gamma term. And this metallicity effect is still consistent with 0 to 1.8 sigma. So clearly the uncertainty is not satisfying. We can do way better. So we need to include more stars of different metallicities. This is why I included the LMC and the SMC. This way we cover almost 1 dex of metallicity. For the LMC, I adopted the distance from Piaczynski based on detached eclipsing binaries, and I corrected the distances of each Cepheid depending on their position in the cloud. I selected a radius of 3 degrees around the LMC center to avoid outliers. And the metallicity of the LMC is on average of 0.34. For the small Magellanic Cloud, similarly, I adopted the detached eclipsing binary distance from GRASIC, and I also corrected for the geometry of the cloud. But since this galaxy is very elongated and has a very long shape, I had to select a radius of 0.6 degree around the center. And the metallicity is 0.7, which is very metal poor compared with the Milky Way. In these 3 samples of Cepheids, I calibrated the Leavitt law. So in red is in the Milky Way, in blue is the LMC shifted by 1 mag, and in green it's the SMC shifted by 2 mag. And the dashed line represents the position of the Milky Way calibration. So from this plot, you can see directly that there is a trend. The more you go to the metal poor, so from Milky Way to the SMC, the fainter is the intercept. So I fixed the slope of this relation to that of the LMC because it's the largest sample of Cepheids. And I represented the intercept as a function of metallicity. So we have 3 points, and I fitted the straight line again with the Monte Carlo simulation, including uncertainties on both axes. And I obtained a negative sign, so consistent with the previous test, but now with a way better precision of, it's really lower and similar with what we have in the literature. So this sign means that metal-rich Cepheids are brighter. And I repeated the same calibration in different wavelengths. So my results are in blue. I find a negative metallicity effect in all wavelengths from the mid-infrared to the optical in Gaia band. Here, the first point is in the 4.5 micron band of Spitzer. It is very special because it has a wide CO absorption band. So the metallicity effect in this filter may be biased. This is why I excluded them. I excluded this point from the fits, and I fitted a line in all the other points. And we can see there is a slight trend. It seems that the near infrared is more sensitive to the metallicity than optical, which is opposite to what was suggested before. Many studies considered that the near infrared is less sensitive to metallicity. In summary, we have used the best distances available in the Milky Way with Gaia and also in the Magellanic Cloud with eclipsing binaries. By including the LMC and the SMC, we have a large range of metallicities. And we confirm a negative sign for the metallicity effect, which is consistent with most other studies. And the result also suggests that the near infrared is more sensitive to metallicity than the optical. And so far, this calibration is the most precise so far, and it should be considered for improving the error budget on the Hubble constant. Some limitations of this study. There are large systematics because of the combination of a large number of filters and surveys for the photometry. The LMC and the SMC samples are important because they provide lower metallicity Cepheids, and just using the Milky Way is not sufficient to get good precision. We only have a few individual measurements of metallicities, and mostly in the Milky Way. So we need to obtain more values and more high-resolution spectra, because for now we have to use mean metallicities, which is quite limiting. Also, the distance to the SMC was measured with eclipsing binaries, but because of its shape, it introduced large systematics on the distance. I will conclude with some perspectives, and I would like to mention two papers to which I have contributed recently. The first paper is about the parallax of pulsation technique. In this method, we compare the angular diameter variation of a star obtained from interferometry or surface brightness relations with the linear diameter variation obtained by integrating the pulsational velocity to derive the distance. But this technique relies on a parameter called the projection factor, or the P factor, which is used to transform the observed radial velocity into the real pulsational velocity of a star. And this parameter depends on the structure of the star and the physics of the star, such as the limb darkening or such effects, and it's still poorly calibrated. So in a recent paper that was just accepted a few weeks ago by Trahan et al., we combined Gaia EDR3 parallaxes for a sample of about 70 Cepheids with the most complete sample of photometry, radial velocity, and well-covered light curves, and also interferometry for some of them. We applied the SPIPS code, which was developed by Antoine Meran, which is an implementation of the parallax of pulsation technique. It feeds all the data simultaneously and returns the P factor. And we obtain no clear correlation between the P factor and the period, or with any other parameters such as the metallicity, the amplitude of the light curves, or anything. So it suggests there is physics behind this projection factor that we still don't understand. And we need to investigate more this physics behind the projection factor if we want to make the parallax of pulsation technique competitive with other methods. Finally, I would like to mention a second paper. In this paper, we would like to carefully inspect one particular step of the distance scale, the second one, the Cepheid distance to supernovae host galaxies. In one particular galaxy, NGC 5584, in these galaxies, the SHOES team has obtained photometry, time series photometry for these Cepheids, and they used these Cepheids to establish amplitude ratio relations, and then they applied these relations to 9 other galaxies, assuming that these relations hold for all Cepheids. We wanted to independently reanalyze the data from the raw HST data and using different software for measuring the photometry, correcting the crowding bias by correcting it locally at the position of each Cepheid, and applying a template light curve creating template light curves on Milky Way Cepheids that are fitted simultaneously with the SPIPS algorithm. And applying these templates, we derive the periods and mean magnitudes in each HST filter for the Cepheids of this galaxy. And in the paper by Javan Mardi et al., we obtained these, we recalibrated these relations, and we obtained the points in blue while the gray markers are from the shoes team. So we obtained a lower dispersion, but also we are in very good agreement. And this relation is also consistent with Milky Way Cepheids. So adopting completely different methods yields a good agreement in terms of magnitude, in terms of periods, in terms of amplitude. So it shows that this is really a consistent work. And finally, we derived the distance modulus of each Cepheid in this galaxy by applying two different PL relations. The first one in the Milky Way, the one I obtained in my first paper, and the second one in the LMC. The one from the Milky Way is in excellent agreement with the one from shoes, while the PL relation in the LMC yields a lower distance modulus, which is what we expect because of the difference in metallicity between the LMC and the Milky Way. Finally, some perspectives for future observations. We have obtained 10 orbits of the HST to obtain spatial scanning photometry for 10 cluster Cepheids. This will allow to avoid the photometric systematic between different systems, since extragalactic Cepheids are also observed with the HST. With the JWST, we also have obtained a program to observe extragalactic Cepheids, and with the great resolution of the NIRCam camera, we will uncrowd the Cepheids, which means we resolve the background contribution from the flux of the Cepheids, which is also a very important systematic in the distance scale. And I'm really happy that I will join the shoes team to work on these two projects. We also are waiting for the next Gaia releases, so hopefully we will get finally precise parallaxes for Cepheids with a better estimation of the 0 point, which should improve the calibration of the PL relation in the Milky Way. And finally, with the next generation of ground-based telescopes, but also space telescopes, we may obtain high-resolution spectra for Milky Way Cepheids, but also Magellanic Cloud Cepheids, and maybe in other galaxies, metal-poor or more metal-rich galaxies, which should improve the calibration of the metallicity effect. And combining all these improvements, we should obtain, hopefully, a 1% precision on the Hubble constant. Thank you.
Thank you very much. This was a beautiful presentation. So now we will ask the referees of your thesis to ask the comments. So Gisela Clementini.
Let me first congratulate for your work and presentation, Louise. Very nice. I have just a few questions or ideas or thoughts, comments. It is true that for the Cepheids you have to use this is a three-step construction of the distance buffer. Could you use also some kind of Cepheids that can allow you to bypass the three-step? Like, for instance, very long period Cepheids, which exceed 100.
Yes, they are the Mira stars, but they are not Cepheids.
I'm talking about Cepheids.
You just talk about Cepheids. If we can observe very long period Cepheids, they would be also very bright. So maybe we can observe them to greater distances. I had never thought of this, but maybe we can observe them in distant galaxies or nearby. And sure, a long period Cepheids are really important, and there is a lack of them in current calibrations. But actually, I don't think it's possible to reach the Hubble flow just with Cepheids. I think they are too faint, but this is just what I think right now. But maybe with new generation of telescopes, we can reach this range of magnitude. So maybe in the next years, it will be possible to observe directly Cepheids in the Hubble flow, which would be amazing.
Because you would bypass one of the problems, that is the calibration.
Yes, the different steps. Yes, and it would reduce the systematics between the different steps, of course.
Well, there are a few long period Cepheids that exceed the 100 days period, like, they reach almost 200 days, but they are very few.
They are very few, and I assume that their physics may also be different than the physics of regular Cepheids.
Well, there is little known.
Yes.
Little known about them, so probably it's something to investigate.
Yes.
That could be a good possibility. Do you want to, go ahead, or do you want
well, just to comment on, so excellent presentation, Louise, congratulations. So we actually have tried to image a galaxy in coma, in the coma cluster for Cepheids. Yes, the analysis of the data has proved challenging, but that would be 100 megaparsecs. And so if we can find some Cepheids and follow them up with James Webb, then maybe we'll be able to get a direct measurement of H0 from Cepheids in the Hubble flow. But then, of course, you have to correct for large-scale flows, so that brings another systematic that supernovae don't have. So something that struck me, a very interesting result on the metallicity relation.
Yes.
So in the olden days, I guess, you had this appealing idea that you had line blanketing in the UV and optical, and that would depress the fluxes of the Cepheids, and that flux has to go somewhere, and so it pops up in the infrared, right? But now you're showing basically that the dependence is negative at all wavelengths, essentially, right?
Yeah.
So what do you think is the physics behind that?
Yes, that's a very interesting question. So first, the line blanketing effect was suggested by Friedman and Mador to explain the trend of the green points, why it goes to the positive sign. So yes, the flux is absorbed in the optical and re-emitted in the near infrared. So here it seems that this explanation is not sufficient to explain this. So I have thought about explanations recently for this trend. And for example, I think we can imagine that the PL relation, when you change of metallicity, the PL relation not only moves on the magnitude axis, but there is a change of period. So it also moves on the horizontal axis. And this you cannot see because you cannot disentangle between the vertical and horizontal movement of the PL relation. You are just comparing these calibrations, but not Cepheid to Cepheid. So this is one idea. But of course, it's difficult to evaluate these movements.
So is this basically a different mass luminosity relation for different metallicities?
Okay, so there is a mass luminosity relation, and it should it still holds. But I think inside the Cepheid there might be effects that are not only in the photosphere, but that might affect the density of the star, and this also might affect the period. So this is just an idea, but I should investigate this to find more explanation of this effect. But it's clearly not just in the photosphere of the star, it's more the physics inside the star.
You change the density, you change the pulsation, and to change the density, you either change the mass or the radius or both.
Yes.
So, great.
Some other questions?
Yeah, well, okay, it has changed.
Yes.
Yes, this discussion brings me to another question I had, and I think I mentioned in my comments. It is certainly, striking that all the observations tend to provide a negative value, empirical measurement tend to provide a negative value of the period luminosity, of the dependence on metallicity of the luminosity relation, while theoretical models, so actually they find the opposite.
Yes.
Do you have an idea, a suggestion for theoreticians also to?
Yes. So when we compare theoretical prediction with empirical studies, we don't compare exactly the same thing, because in the models, they compare one Cepheid, for example, and they change the parameters, the metallicity of one Cepheid to see how it evolves. But here, empirically, we cannot modify the parameters of one Cepheid. So we compare basically the PL calibrations, actually, not the Cepheid between themselves. So we have to take high metallicity Cepheids and low metallicity Cepheids and compare how the PL relation behaves. So this is not exactly the same thing that we are doing to calibrate the metallicity effect theoretically and empirically.
Would that mean in a way that you are not comparing exactly the same quantities? That's or
I mean, empirically, we can only observe what is visible from in the PL relation, but we cannot see inside the star what we can see in the models, for example. We can see only the impact of metallicity on the luminosity, but with models, it's more, maybe it's more precise. We can go deeper in the physics, while empirically we just see the results of this change of metallicity.
So how do you have an idea or a suggestion of what would be how would be the way to bridge these two? Because, you know, it's a bit, you know, hard-worked.
I think there is a hard work for the theoreticians to, I don't know, work on the models and understand better. I don't know if there are things we have not thought about yet. And empirically, what we can do is just compare the PL relations and use more data with a larger range of metallicities to have a more precise value and yes, understand the trend, if it's dependent on the wavelength or not. But yes, for now, it's really different from what we get from the models. So there is work for both sides.
Thank you. So, Professor Macri?
Yeah, so in the third paper that you mentioned with the parallax of pulsation,
Yes.
You seem a little despondent about the result, but at least there is a nice trend with log P, no? So
there is a slight trend indeed, but we expected a lower dispersion. And actually, the dispersion is not due to the data, but to the physics of the projection factor. So this is mostly the result of this paper.
Is there any hint as to why, at least to the eye, it seems like there's larger dispersion below 10 days?
Yes, and we would like to investigate this by including a shorter period pulsating stars and also MIRAs at longer periods to see how these relations looks like when you zoom out and to see if indeed there is a smaller dispersion at longer periods, or if the problem is just for Cepheids with short periods. They have maybe a bump or something on the light curve that explains that the projection factor is not the same. So this is really interesting, and in our Gaia project, we would like to investigate this projection factor.
To investigate that, it would probably add anomalous Cepheids to the sample. They have a bump before minimum.
Yes, and we need a lot of data and complete light curves and radial velocities to study this parameter.
Some of them should become available with Gaia DR3.
Yes, we expect that.
Another question I had, actually, it's more an idea. So you are comparing the period luminosity relation or the period asymptotic relation in the Milky Way, the LMC and the SMC, and then you combine them because otherwise you won't have enough metallicity range.
Yes.
But this means that you assume, as everybody, that there is a universality of the period luminosity relation.
Yeah.
And that's a big assumption. We cannot do much more than that. Or probably we should look for metal poor Cepheids in the Milky Way, if there are any.
If they are.
So what do you think? You know, how good is this assumption? Well, actually, we are kind of forced to make such an assumption, or is there a way out? Or
yes, we are forced to make this assumption. The main one is to fix the slope of the PL relation to that of the LMC. But some studies suggested that the slope is different in different galaxies. So this is a big assumption. We also assume that the slope is the same for all Cepheids, but there might be a break at log P1. So we should also run this analysis by assuming different things with adopting different slopes. And I tried to make different tests, like fixing the slope to that of the Milky Way or to the SMC instead of that of the LMC. And it does not change the result significantly. So this is a big assumption, but for now, this is all we can do. But of course, yes, we have to make these simplifications because we use different samples, different galaxies. We could use the same galaxy if we find metal-rich and metal-poor Cepheids in the same galaxy. But it's difficult because if you go to greater distances, we cannot measure high-resolution spectra, but you have to use the metallicity gradient, and it can be less precise. I mean, it is less precise than the spectral metallicity.
At least in the outskirts of the Milky Way, where you might find lower metallicities, presumably the Cepheids are faint enough that you would get better parallaxes, so that could help you to make a differential measurement within the Milky Way. Yes,
because we would have Gaia parallaxes, but we need a extremely good precision on the metallicities. And for now, the individual metallicities are not precise enough. So we are waiting for a paper on new metallicities for LMC Cepheids, and probably we will have more details soon. But yes, high resolution spectra are really important for this analysis. I didn't mention that enough, but we really lack of metallicity measurements.
You'll be glad to know that paper was submitted yesterday.
Okay, thanks.
Yes, there is also work in progress by the team of Ripet et al. They have many spectral Cepheids in the metal-poor regime, so it should become
interesting.
soon. Yes, it's some work in progress on that, because definitely, you know, to have a sample of Cepheid in the Milky Way that covers the some that, you know, the whole range of metallicity, that would.
But we need a good precision on the metallicity, as I said, but also a large sample of Cepheids, because just a few of them is not enough.
So maybe one final small question. When you had the plot of the three galaxies and the metallicity relation, you later alluded to systematics, which I guess are not included in this uncertainty.
Yes, there are systematics here. Like on the intercept, there is the photometric systematic, because we use different systems. You know, there is not one survey for SMC, LMC, and Milky Way Cepheids. So I included a quite large systematic. I don't have the number in my mind, but I added quadratically to the uncertainties this systematic to take into account the different photometric systems.
So that's already on the error bar.
And it's here in the, yes, it's included here.
Right.
Okay, so thank you very much. Now we are passing to the virtual jury.
Yes.
So Massimo Marengo, do you hear me?
Yes, I do. Can you hear me now?
Yes.
Okay. So first of all, I would like to congratulate you, because reading your thesis was really a pleasure. It's really well written, and you've done a very careful work in examining all the, the potential problems that the data have. So I really enjoyed it. And I do have some questions, mostly curiosity that I have after reading your thesis and listening to your talk. So one question I have, for example, is going back to the issue of the universality of the PL relation. Having more data on the Milky Way, certainly on a larger range of metallicity, certainly would be useful. My experience with RLR is that, however, data in the Milky Way is not just an issue of getting accurate metallicity, but also the weight of the precision of the parallel axis is more important, because it really scatters the even smaller error. It contributes to significant scatter in the absolute magnitude that you need to fit. On the other hand, you have two other galaxies in your study, the two Magellanic Clouds, that provides points which have a good leverage in metallicity. Have you considered adding other galaxies to improve the precision of one side, measuring the metallicity term, but also on the other side, fitting the slope of the peer relation, given that all those, yes, there are some geometrical factor, but are much less than the one that you can have for individual stars in the Milky Way. And there are, for example, other spirals in the local group, but also some dwarfs also that they have Cepheids. For example, we are publishing now a paper on VV124, which has all sorts of different variables, including some Cepheids in the central area. So have you considered expanding your sample to galaxies, to some with other galaxies in the Milky Way, in the local group with a lower metallicity?
Yeah, thank you very much for these comments. So yes, I have considered, actually this is the next step of this analysis. I have already extended the range of wavelength, and now I would like to extend the range of metallicity. In the Araucaria project, we have, they have measured distances to some galaxies in the local group with a very good precision. And some of them may be very metal poor or metal rich. So having these distances to these galaxies, we should try to include them into this analysis to add more points to this plot. We have only 3, but yes, of course, this is the next step of this paper. And your other question, can you repeat? I think it was a very long comment. I don't remember all the questions.
No, that was the question. The other was mainly a comment. Basically, if it's not just getting more point on that plot to measure better the intercept, but also you can, with all the given that they are more or less at the same distance, especially if you go to smaller galaxies, you get the slope in one shot. You don't have to take into account the differential distances within the galaxy, because that would be small compared to the distances to that galaxy. So that will also allow you to investigate the universality of the period slope across galaxies with different metallicities. So that was more a comment more than a question. Of course, when you deal with those galaxies, the metallicity of the Cepheid population is not necessarily the same as the one of the galaxies as a whole. So you will need to, you still need some spectra to be able to see what is the metallicity of the Cepheids with respect to the one of the older population that is the bulk of the stars in those, at least for the dwarfs. I do have another question. One thing that would be quite useful for people that are doing models of Cepheids, pulsational model, is to get some idea of the experimental width of the instability strip. And you mentioned that with your PL relations, you actually have reached a point in which it seems that the residual dispersion is in large part due to the physical width of the instability strip, which ultimately is a temperature effect, right? So, but you also have the dependence of metallicity. So have you tried to decouple the two effects to understand how much of that dispersion that you have in the peer relation, I'm talking about the first part of your thesis, is due to what could be the intrinsic weight of the instability strip, and what instead of the residual effect due to the dispersion in metallicity?
Yes, I neglected this effect because I fit only the period luminosity relation. But if we want to see more what is behind this width of the instability strip, we should include the color term, which is similar to the temperature. And yes, I didn't do it in my analysis because I didn't have enough stars, especially in the first paper with companions and clusters. But yes, we should calibrate also the color term of the period luminosity color relation. This should help to understand more about this calibration and reduce the dispersion.
Okay, thanks. Regarding the color term, in fact, I've seen works in the past, like the work of Laura Ino, showing how it was expected that the Wazen-Height relations would be less sensitive to, have lower dispersion, not just because of the, you remove most of the dependence on the extinction, but also because this color term kind of magically also reduces the effect of temperature and the effect of metallicity. And I see you did calculate a couple of Wazen-Height relation in the second part, to see what is the effect of metallicity. And did you see that is smaller, like in this previous work, or is not the case?
Thank you for this
the
question.
Wazen-Height.
Yes, I could not represent the Wazen-Height on this plot because it doesn't have a single wavelength. But the Wazen-Height index in the infrared, combining the J and K band, gives also a negative sign and very consistent with the J and K effect, so 0.2. And in the optical, it is also a very strong effect, a bit lower, but if I remember correctly, 0.15, still in the negative. So it doesn't seem that the metallicity effect is weaker in the Wazen-Height.
It's interesting, yeah. In RLI, we do observe that it's weaker. So it's interesting to see that in Cepheids it's not. Okay. Well, talking about RLI, do you think that these techniques can be extended to RLI? Especially, a lot of the data we have for RLI are in a globular cluster, which are different than open clusters, so they have different systematics. But do you think, what kind of problems do you think may be in trying to do this kind of work to older population where the pulsators are the RLI?
Do you mean
open-ended?
Do you mean for the metallicity effect for this analysis, or?
Yes.
These stars are more metal poor, and it's more complicated to calibrate this effect because there is a metallicity luminosity period metallicity luminosity relation. So I did not work on these stars at all. But I think it's more complicated to calibrate these relations because the metallicity has a very is very poor. So I think there are more effects to be taken into account. There is the Blasco effect, and I know the light curves can be different. So I have not worked on these stars, but I think there might be some difficulties to obtain a metallicity effect, and we should take into account all the effects that are known, such as the Blasco or such effects. But it might be possible. It's interesting, and yes, the metallicity. I think there is also a very strong term in metallicity for these stars.
It is maybe not stronger for individual stars, but you have a much larger range of metallicity. So let's say it's a more important effect when you're trying to use them for distances because of the larger dispersion. So yeah, I agree with you. So one thing that we did with RLI is there is a dependence of the shape of the light curve on metallicities. And it's not something that you can use to get very accurate metallicity for individual stars, but it's something that you can use to get metallicity of populations. And you do have pretty good light curves and pretty good value of metallicities. Have you tried to do something like that? Basically, you get a relation between Fourier parameters, some combination of Fourier parameters of the light curve and the metallicity. Is it something that you think you can do?
Do you mean for Cepheids to compare the shape of the light curves with the metallicity?
Yeah, we know that it works with other pulsators, but I was wondering if you or somebody else tried to do that with Cepheids?
No, I haven't tried, but it could be interesting to check. We have very well covered light curves for Cepheids, so this is possible.
Yes, I knew that you were going to answer.
Okay, so thank you.
I would like to comment on that because, you know, what is lacking? We lack metallicities for individual Cepheids in the Magellanic Clouds. So we started to do that, and we have very good preliminary calibration. So it works for the Cepheids as well. But the range of metallicities in the Milky Way is not large enough. So we are waiting for individual metallicities for Cepheids in the large Magellanic Clouds, and then we will be able to do that, to calibrate this relationship. And it works. It looks really promising.
That's good. Okay.
And
I'm done with questions. So if you want to go on, yeah.
Just a comment on your last discussion, Massimo. There is a relation that has been established for Cepheids with period shorter than 6 days. This relation was established, relation between Fourier parameters and metallicity. This has been defined by Laszlo Zabatos and colleagues, and we have tried to use it to infer metallicities of Cepheids in Gaia. But, you know, it's not that well defined. I mean, it's not that stable, but there is some.
Okay, so now we have two invited people in the jury. Adam Reis, do you hear me?
Yes. Can you hear me?
Yes, yes.
Okay. Louise, a very nice talk. It was extremely clear, very well presented. I really enjoyed it.
Thank you so much, Adam.
So I have a few questions. So first, I wanted to bring up this issue of the universality of the period luminosity relation. So I'm not totally sure what exactly picture we have in our mind when we're talking about that. But I think empirically, people are often talking about the slope of the period luminosity relation. Now, you said that in your work that's an assumption about the universality, but I was looking at your tables, table 3.3, and you independently measure the slope of the period luminosity relation in these 3 different galaxies, the Milky Way, Large Magellanic Cloud, and Small Magellanic Cloud, that span this large range of metallicity. And it looks like to 1 sigma and pretty high precision that they all agree quite well. So I'm looking at your H band, and it's like 3.15, 3.14, 3.18, and, you know, with error bars that are consistent with that. So I guess my question is, what do you mean by the universality? And is it something you're assuming, or is it something you've tested in your thesis?
So thank you for this question. So I had to fix the slope to obtain the metallicity effect. So the test was first to see if the slope was different in these 3 galaxies. So as you mentioned, they are quite consistent to 1 sigma. And the tests I have done were to fix the slope to that of the Milky Way, and then to that of the LMC, and then to the SMC, to derive the gamma term, and the results are almost the same. So negative sign, 0.2. So this assumption of the universality was tested this way. And at the end, it's a big assumption, but it's justified by the fact that it doesn't change the gamma term if you change a little bit the slope of the PL relation. The difference in intercept is still showing this trend.
Okay, I mean, from my way of looking at it, if the slopes did not agree, that would mean the universality failed. And you know, while you can always have higher precision, it looks like your measurements of the slopes independently confirm, at least to this precision, the universality. Okay, let me move on to my next question. So sticking on this figure, the question of how well you can constrain the metallicity effect at least empirically, is a very, I would say, simple proposition of what is the baseline or range of metallicities you're using in your analysis. And I think you've done the best that you can do, because you've gone all the way from the Milky Way to the SMC, which is a full DEX. And so one DEX, which I think you've seen in your analysis, gives you a precision in the metallicity term of about 0.05. When you just did this within the Milky Way, where the dispersion index is about 0.3, so, you know, quite a bit smaller, you got to only a 10th, 0.10 in the metallicity. So what I want to ask you is to explain, looking at this plot, the green points from Friedman, they came from measuring only internal to the LMC, and the dispersion of those metallicities is only 0.1. So I guess in the direction of clearing up this difference or discrepancy between your measurements and those with Friedman, particularly in the H band where those errors are very small, how can the errors be so small in those measurements versus your measurements?
Yes, that's a good question. And actually, you are right. They use, if I remember correctly, they use only LMC Cepheids with individual metallicities, and also a small number of LMC Cepheids. So I also wonder how these uncertainties can be so small. So I think I should read the paper in more details, but I think there might be something behind these points. So yes, the K band and H band are not really sensitive to the reddening, but regarding the distance and the range in metallicity, obviously, it cannot be so precise.
Okay. I mean, I think it's, you know, certainly I understand your research is to make the best measurement you can, but then, you know, when you're done and you see these discrepancies, it's important, I think, to reflect back on, you know, why is there this discrepancy? How could these disagree? And sometimes revisiting past analyses, I think, could be important. In your case, I mean, I'll just say I've gone back over your measurements in your thesis because we're going to use this for the shoes analysis, and I'm getting the same results as you get, and I'm getting the same uncertainties that you get. I can tell you it's not possible to get those small uncertainties from internal to the LMC because the span of metallicities is just not very large. This paper by Martino Romagnello that I think just got submitted yesterday, he's now measured 90 of these metallicities, including all the shoes Cepheids, and the dispersion is consistent with the measurement uncertainties, meaning you can't even tell that there are different metallicities within the LMC. And so I don't think, you know, I think what you've done is the right thing to do, is to go between the clouds and the Milky Way and things like that. It's too small a span within to get much from that. Let me ask you another question, which is, ultimately, you can make these great metallicity measurements, but then you want to connect them to metallicities for Cepheids in distant galaxies, where we generally don't have spectra. So how is that done, to your knowledge, and how consistent is that with what's done locally, the metallicity measurements in distant galaxies?
Okay, thank you for this question. So to my knowledge, in distant galaxies, as you mentioned, they cannot measure spectra, but they use a gradient in metallicity from the center to the outer regions of the galaxies. But I don't think the gradient is well calibrated. I mean, this is not as precise as individual metallicity measurements from spectra. But for now, this is all we can do. But maybe in the future, we can measure more spectra in nearby galaxies. So yes, for now, using metallicity gradients is what we can do. This is, to my knowledge, this is how it's done. But maybe there are other techniques.
What is this? What are the spectra of in the distant galaxies?
Because we cannot measure spectra of one Cepheid individually, but we have to resolve from the crowding. There is a problem of crowding also for spectroscopy.
But what are in the distant galaxies, we take a spectrum. Is the spectrum of stars? Is it of other objects in the galaxy?
Yes, if we take a spectra of a region of a galaxy, it includes the dust, other stars of different types, and the Cepheids. So we have to know if the Cepheids are the same as other stars, and if the metallicity that we measure from these spectra represents the metallicity of the Cepheid that we are observing.
Okay. I'll add in some information that generally we can't take spectra of individual stars, at least not yet in these distant galaxies. So we usually take the spectra of H2 regions in these galaxies. We measure strong lines and convert that or calibrate that to metallicity, but it is a different way of doing it than the spectra directly of Cepheids. So that's the thing just to think about when we think about all these steps and uncertainties. Very good. Trying to think if I had any other questions. One thing I wasn't 100% sure of, and I'll have to go back to the history of this. I know that Hubble observed Cepheids in M31 to determine that it was indeed outside the Milky Way. You mentioned, and I'm not saying this is right or wrong. I have to go back and remember whether all of his distance measurements for his first Hubble diagram came from Cepheids, or instead if they came from things he called the brightest stars in galaxies. You said Cepheids. I'd be happy for Cepheids to take the credit, but I'm not sure if that's right. You might, if you give this talk again, you might look that up and double check.
Yeah, thanks. I think you're right. I'm not sure he observed Cepheids in distant galaxies. It doesn't make sense. Probably it's brighter regions or different stars.
Right. I think it was actually even H2 regions and things like that, yes. Which wasn't crazy for 1927 or 29. But anyway, okay. Well, thank you. I really enjoyed your presentation.
Thank you, Adam. So we have another invited, Gregor Pietensky. Do you hear me?
Yes, I do. Well, I would like just to echo other members of the jury. Well, I enjoyed very much the thesis and the presentation, and I think this is of very high quality. And most of the questions I would like to ask have been asked already, so it's an easy job for me. I would like just to add one. Louise, what is the perspective to calibrate the metallicity effect on Cepheid brightness, just based on one galaxy? You mentioned that we have gradient of metallicities in different galaxies, especially in spiral ones, right? So our Milky Way galaxy could be a good laboratory to calibrate this effect. From your point of view, what would be the precision and possibility to calibrate this effect just based on Milky Way Cepheids?
Okay, so what I have done in my thesis, when I just use the Milky Way, this is the precision I obtain on the metallicity effect, but from the current distances from Gaia and the current metallicities. But if we improve parallaxes with the new data releases, for example, in 1 or 2 years, or maybe more, and we have more individual metallicities in the Milky Way, we should improve this precision. But I still don't think the Milky Way only is sufficient. I really think adding other galaxies is really important. And also working on the photometry could be important to reduce the systematics on the different surveys, different filters. So maybe use the same instruments to observe different galaxies. If we find metal-poor galaxies, or even between the LMC and the SMC, make a global catalog which would cancel the systematic on the photometry. That would be interesting.
Okay, thank you.
Okay. So maybe I'm the last member before. So I agree that your thesis was a very huge work and very carefully done. And I enjoyed a lot reading the thesis, even if I'm not in the domain exactly. But the presentation was very clear also, so very, very interesting. And since all questions have been asked, I will just make a reflection on this. I was surprised to see how dispersed are all these values. And since all you showed in your plot that are all in the vicinity of the sun, in fact, they are. So why are there so, in fact, 0.3, 0.8 decks? Maybe are there some migration of stars? You think that you have not the right metallicity gradient on Cepheids, that they can have migrate from the center to the other parts or whatever?
I'm not sure about the movement of the stars inside the Milky Way. I would think more of error of calibration for the metallicity values, I think.
But if the error is so large, so you should make an average of this, I think that it's still...
This is why later I adopt the average metallicity for the Milky Way, because I did not trust the individual values.
And for external galaxies, the gradient is a problem also.
Yes.
Also, I noticed that after that, you have calibration with the masers before the supernovae one and so on. And you mentioned a lot 4258, which is very well known. Are there other masers? Because there are about a dozen masers that we are known. So can we improve this passage of calibration and using more masers?
This is a good question, but honestly, I have not studied the masers, so I cannot answer your question.
Yes, okay. So I will now give the word to Pierre Vela, the supervisor.
Thank you very much, Françoise. So I don't have questions. I mean, we worked together for quite some time already. I just wanted to mention that I know you since quite a long time, because we had the pleasure to work together already during your Master 1 thesis, so in Chile at the time, and it was really a wonderful work already at the time. What I can say is that I've been extremely pleased to supervise your work, to work with you. It was really a pleasure, and I appreciated a lot your work. I mean, you really made an exemplary work with a lot of rigor and enthusiasm, and this was these are really the qualities of a good researcher. I'm sure that you will have a future full of beautiful discoveries. And well, there's not much more to say. I'm sure you will have a very nice future, and I'm pleased to see your excellent results during these 3 years that we spent together. So thank you, Louise.
Yeah.
Thank you, Pierre. So now we are going to deliberate. And I guess that all the people have to leave the room because
Françoise.
Oh, yes, of course. Before leaving,
1 second.
Before everyone is going somewhere else, I would like to say a few words just quickly. So I would not become a doctor today without the help of many people. First, I would like to thank Pierre Vela with all my heart for inviting me to join you in Chile when I was in master. It was a great time, and thank you for inviting me to continue my work with you during this PhD. You have been a very good teacher. Thank you for your support and being here for me. And I really, honestly, I have spent the best 3 years of my life during this PhD. I would like to thank the jury members, Françoise Combe, Lucas Macri, Gisela Clementini, Massimo Marengo, Adam Rees, and Gregor Piotrowski for accepting to evaluate my work. I am very impressed to have you in front of me. This is really a pleasure to discuss with you today. I also have wonderful colleagues that I would like to thank, and the Gaia project, of course. I would like to thank Wolfgang Gieren for always supporting me and reminding me that the world is beautiful outside of my computer screen. I would like to thank Antoine Meran, Nicolas Nardetto, and Benam Javan Mardi for reading my PhD manuscript and helping me to improve it. I thank Gregor Pietrzynski, Piotr Wilgorski, Alexandre Galen, and all the members of the Araucaria project, Jesper Storm, Giuseppe Bono, Vincent Ogde. And of course, I would like to thank Marek, Mikołaj, Darek, and Bartek for sharing with me the responsibility of Cerro Armazones Observatory for a few nights. It was a pleasure to be on top of this mountain and to walk on the construction site of the ELT. I think it's a great privilege. I would like to thank all the people who have helped me, inspired me, and supported me. Adam Rees, thank you for sending me the first email when you saw my poster in Chicago, and thank you for spending so much time on helping me to improve my results and the calibration of H0. I would like to thank Richard Anderson for a very good advice and very kind support. Frédéric Arenou, who is not here, but I thank him for teaching me so much about Gaia, especially this last month. I am also very grateful to Wendy Friedman and Barry Medor for giving me very important advice. And I will always remember sharing an ice cream with them in Chicago by the river. As a first-year PhD student, this is very impressive. I would like to thank Keegan for reading all my manuscripts and noticing all the English mistakes. Thank you. But also Vincent Coudet du Foresto for all the support. I thank Brigitte Roca, who was my supervisor for my first astrophysics internship at IAP 5 years ago. Thank you for showing me that research is wonderful and convincing me to continue on this way. I had a lot of amazing teachers, but I cannot name all of them. So I would like to thank one, Alain Abergel, thank you. And I thank Joanne Breitfelder, who is here today, because she gave me the contact of Pierre Carvela about 6 years ago. I was looking for an internship, and she said, if you want to go to Chile, maybe you can contact Pierre. So if I'm here today, this is thanks to you. I am very lucky because my friends have always supported me and believed in me. Marie, my oldest friend, Barbara, François, you are my family. My Greek sister, Katerina, Marvin Dupuis, Aurélien, Dany, Pierre Guillaume, Gabriel, from Orsay, Natalia, but also Guillaume. And I know many of my friends are also watching my defense. So Juliette, Julia, Anaïs, Camille, and Joanna, thank you for all the support. I was also very lucky because my parents and my sister and all my family has always supported me. Thank you for giving me the opportunity to study physics in Paris and to always follow my dreams and for believing in me. And I will just finish with you, Boris. Thank you for being this amazing boyfriend, and you have always believed in me, listening to me talking about Cepheids at 11 p.m. almost every day. And you are my best co-author, my best colleague, my best friend, and even more, and I love you. Thank you.